Hello, everyone, and welcome back to PodBites, where we break down complex medical topics into bite sized pieces. Perfect for your commute, coffee break, or whenever curiosity calls. I'm Saad, your host for today's episode, and I'm joined by Yahia. And together, we're going to go on a metabolic adventure, talking about something that powers every single cell in your body, from the sugar in your morning coffee to the ATP that makes your heart beat. We're tracing the full epic journey.
Exactly, Sad. This episode is all about glycolysis, the TCA cycle, and the electron transport chain. We'll go step by step. How glucose gets into cells, how it's broken down, how energy is captured, and what happens when things go really, really wrong.
Okay, so Yahya, before we start, let's imagine a scenario I think me and you, or a lot of us, can even relate to. Imagine it's Saturday morning, you're on your Ashton Hall grind set, going on a run, maybe to better your life. Or maybe you drank too much boba tea. 500 calories, by the way.
Been there?
Right? So you start running, first few minutes, you're fine. But then maybe 20 minutes in, your legs start to burn, you're breathing harder, that familiar burn sets in. What's actually happening inside your muscle cells at that moment?
That's the perfect entry point, Sad. What you're feeling is a shift from aerobic to anaerobic metabolism, when your cells start making energy without oxygen. But to understand why that happens, we need to start from the very beginning. What is metabolism, and how does your body decide whether to store energy or burn it?
Okay, Yahya, so let's lay the foundation. Metabolism. It's a word we throw around a lot. But what does it actually mean at the cellular level?
Think of your cell as a tiny, bustling city. Metabolism is the sum of all construction and demolition projects happening at once. There are two main types. First is anabolism, which is the construction or building things up, which requires energy which comes in the form of ATP. Then there is catabolism, which is the demolition or breaking things down, which releases energy that gets captured as ATP.
Okay, so it's a constant balance. And these processes aren't random, right? They're organized into pathways.
Yes, of course. Metabolic pathways are just a recipe. You start with the raw ingredients, let's say glucose, then you follow steps and end up with a dish, while the kitchen tools, let's say the enzymes, make sure it all goes smoothly.
Okay, I like your analogy, but you can't uncrack an egg. But I do know that some of these processes are reversible and some are not, right?
Right. The irreversible steps are the big one-way gates. They're usually the ones that are highly regulated, and one step is usually the slowest, the rate limiting step. It's like the narrowest point in a funnel. It controls the speed of the whole pathway.
Okay, I like the analogies, but give me a real example.
Okie dokie. In glycolysis, the breakdown of glucose, the rate limiting step is catalyzed by an enzyme called phosphofructokinase 1, or PFK1. If the cells want to speed up or slow down glycolysis, it adjusts PFK1.
Wait, adjust? How does the cell adjust an enzyme? Do they have little remote controls?
Almost. There are three main ways. Either change how much enzyme is made, and this is effective for long-term regulation, or use covalent modification like adding or removing a phosphate group. This is like flipping an on and off switch. Or by allosteric regulation. This is a big one. It's like a dimmer switch. A molecule binds to the enzyme at a spot other than its active site and changes its shape, making it more or less active.
Allosteric regulation, that sounds a bit fancy. I don't really understand words that are longer than 5 letters. Can you please break it down for us, Yahya?
Sure thing, Sad. Enzymes have two sites, an active site and an allosteric site. The active site is where the actual process happens, while from the name, the allosteric regulators bind to this allosteric site, where they can affect major pathways. It can either make the enzyme more active or less active depending on the situation.
Okay, I love that. And what specific molecules act as these allosteric regulators?
Often it's the cell's energy status, high levels of ATP. That's the signal that says, we have plenty of energy, man, slow down the breakdown pathways. ATP acts as an allosteric inhibitor in that case. High levels of ADP or AMP, that's the signal that says, energy is low, man, speed things up. They act as allosteric activators.
Okay, I like this concept, the energy status concept, but it obviously has a name, right?
Yes, the cellular energy charge. It's the cell's internal fuel gauge. It's primarily the balance of ATP, ADP, and AMP. This gauge is constantly monitored to decide whether to burn fuel or save it.
Okay, but my body isn't just one cell. How do my liver cells know that I just ate a bagel or bit shawarma, and my muscle cells know I'm running?
Great question, Sad. That's where hormones come in. They're the body white texting system. Insulin is the fed state text. It says, hey everyone, glucose is high. Store it or use it, please. Glucagon is the fasting state text. It says, Glucose is low, guys. Start making and releasing it. Epinephrine or adrenaline is the stress exercise text. It says, mobilize all energy reserves now.
All right, ladies and gentlemen, let's take a quick checkpoint before we move on. So, Yahya, imagine you're looking at a metabolic pathway diagram. One step in the pathway is irreversible, highly regulated, and target of allosteric activators and inhibitors. Based on what we've learned about the pathways, what is the step most likely to be? A, the first step of the pathway. B, a reversible step in the middle of the pathway. C, the rate-limiting step of the pathway. D, the final step that produces the end product. Now, Yahya, take a second to think this one through.
So the answer is C, the rate limiting step of the pathway. The description, irreversible, highly regulated, and the target of allosteric molecules is the textbook definition of a rate limiting step. It's the major control point where the cell puts the brakes on or hits the gas. In glycolysis, that enzyme is PFK1.
Exactly. It's the bottleneck. Control that one step, and you control the flow of the whole pathway. Good job, Yahya. Awesome sauce. So now that we set the foundation for what metabolism actually is, let's follow our hero molecule, glucose. It's floating in your bloodstream after that bagel or after that bit shawarma. How does it even get into the cell to start this process?
Glucose can't just walk through the cell's fatty membrane. It needs a door. Those doors are called GLUT transporters. They're like specific gates for glucose, and different tissues have different types of gates.
Okay, give me the tour.
So GLUT1 and GLUT3, these are like high security, always open gates in places that always need glucose, like your brain and red blood cells. They have a low Km, meaning high affinity. They grab glucose tightly even when blood levels are low. GLUT2, this is the liver and pancreas gate. It's got a high Km, or a low affinity, but a high capacity. It's lazy when glucose is low, but can move a ton of glucose quickly when levels are high after a meal. In the pancreas, it acts as a glucose sensor. GLUT4, this is the insulin-dependent gate in muscle and fat cells. When insulin is high, it's like the manager calls more GLUT4 workers to the surface, opening more gates to let glucose in.
So in type 2 diabetes, for example, when there's insulin resistance, it's like the manager is calling, but the GLUT4 workers in the muscle just aren't listening, right?
I wouldn't know, I'm unemployed. Nevertheless, perfect analogy, Saad. Now, once glucose is inside, it's trapped. The first enzyme, hexokinase, immediately adds the phosphate group from ATP, turning it into glucose 6-phosphate, G6P. The negative charge means it can't go back out the gates.
I've also heard of something else called glucokinase. What's the difference?
I'm really glad you brought this up. Hexokinase is in most tissues. Glucokinase is the liver and pancreas version. Hexokinase has a low Km or a high affinity, feedback inhibited by its own product, G6P. It's careful and efficient. On the other hand, glucokinase has a high Km or a low affinity and is not inhibited by G6P. It only gets busy when portal vein glucose is really high after a meal. This lets the liver act as a buffer, soaking up excess sugar without getting clogged.
So the liver basically monitors and regulates the body's glucose storage?
Exactly. In the fed state, the liver stores glucose as glycogen. In the fasting state, it breaks down glycogen and even makes new glucose through gluconeogenesis to ship out to the brain and RBCs.
All right, glucose is trapped and phosphorylated. So what's our next big move?
We go through a couple of steps to rearrange things, and then we hit the major control point. Step 3, phosphofructokinase 1, or PFK1.
The rate limiting step.
Bingo! PFK1 takes fructose 6-phosphate and uses another ATP to make fructose 1,6-bisphosphate. This is the committed step. After this, the molecule is locked into being broken down for energy in glycolysis.
And how is that crucial enzyme controlled? Hit me with the regulators.
Well, we have allosteric inhibitors such as ATP, and that's the high energy signal. It tells the cell to slow down glycolysis. And citrate signals that the TCA cycle is full. Allosteric activators such as AMP, and that's our low energy signal, it tells the cell to speed up glycolysis. And in the liver, something super important called fructose 2,6-bisphosphate, or F26BP.
Fructose 2,6-bisphosphate. That's a mouthful. Why is it so important for the liver?
Because its levels are controlled by hormones. This is where theory meets the body. After a meal, insulin is high. Insulin tells the liver to turn on an enzyme called phosphofructokinase 2, or PFK2, which makes fructose 2,6-bisphosphate. High F26BP strongly activates PFK1, turning glycolysis on to process the incoming glucose. On the other hand, during fasting, glucagon is high. Glucagon turns on fructose bisphosphatase 2, which breaks down F26BP. Low F26BP means PFK1 isn't activated, so glycolysis turns off and the liver can focus on making new glucose instead.
That's even more of a mouthful? Whatever. So after PFK1 commits fructose 6 phosphate to the pathway and turns it into fructose 1,6 bisphosphate, we split that molecule in half, right? What's the name of that split again?
That split is the work of aldolase. It cuts fructose 1,6 bisphosphate into two different 3-carbon molecules. One is dihydroxyacetone phosphate and the other is glyceraldehyde 3-phosphate. They eventually both become glyceraldehyde 3-phosphate, but that's a little enzyme dance for another time.
Okay, so now we have glyceraldehyde 3-phosphate. That's the starting point for the payoff, right? So what's step 6 all about?
Step 6 is massive, just like the low taper fate.
Just get to the point, man.
Alright. It's where we start capturing energy in a form we can use later. The enzyme is glyceraldehyde 3-phosphate dehydrogenase, GAPDH for short. It takes glyceraldehyde 3-phosphate and adds an inorganic phosphate. Not from ATP, just one that's floating around in the cytosol. And in the same move, it uses a molecule of NAD+ to grab high-energy electrons.
So what's the input and output here?
So we're inputting glyceraldehyde 3-phosphate plus inorganic phosphate plus NAD+, and outputting 1,3-bisphosphoglycerate, 1,3-BPG, plus NADH. That 1,3-BPG is key. It's a high-energy molecule with a phosphate group that's just itching to be transferred.
NAD plus and NADH, I hear about them all the time. What are they really?
Think of them as electron shuttle buses. NAD plus is the empty bus. When it picks up electrons and a proton, it becomes NADH, the full bus carrying high-energy cargo. The cell desperately needs to get that cargo to the mitochondria to make lots of ATP, and get the empty bus NAD plus back to keep glycolysis running.
Okay, and what determines how we get the empty bus back?
Oxygen. This is the critical fork in the road. If oxygen is present, aerobic environment, the full NADH bus drives to the mitochondria, drops off its electrons at the electron transport chain to make loads of ATP, and comes back out as empty NAD+. Pyruvate, our other product, also goes to the mitochondria for more processing. More on this later. If oxygen is not present, we call this an anaerobic environment. The mitochondrial ATC is closed. The NADH bus has nowhere to drop off its electrons. If it stays full, glycolysis grinds to a halt because step 6 needs empty NAD+.
Okay, so what's our emergency plan in this case?
The cell uses a backup enzyme, lactate dehydrogenase, or LDH. LDH takes the pyruvate and uses the electrons from NADH to convert it into lactate. In the process, NADH becomes NAD+ again. It's like the full bus empties its cargo into a temporary storage locker, lactate, so it can go back to work as an empty bus.
Oh, so that's the burn in my muscles. Lactate building up.
Precisely. It's a brilliant short-term fix. It keeps glycolysis running, producing a little ATP, net 2 per glucose, when you have no other option.
And that brings us to step 7, the first time we actually make ATP in glycolysis, right?
Yep. Step 7 is phosphoglycerate kinase. It takes that high-energy 1,3-bisphosphoglycerate and uses it to turn ADP into ATP. This is called substrate-level phosphorylation. ATP made right there in the cytosol, no oxygen or mitochondria needed.
And what are the reactants and products for this one?
Alright, so we're putting in 1,3-bisphosphoglycerate plus ADP and getting 3-phosphoglycerate plus ATP. Oh, and here's a fun clinical side note for you, Saad. In red blood cells, some of that 1,3-BPG gets diverted into making 2,3-BPG, which helps hemoglobin release oxygen more easily to your tissues. Pretty cool, huh?
I mean, this would have helped me in my heme exam, but yeah, sure. So after a couple of rearrangement steps, we get to step 9, analase. What's special here?
Well, analase takes 2-phosphoglycerate and removes a water molecule, making phosphoenol pyruvate, or PEP for short. PEP is super high energy, even more than ATP. But here's the high yield twist. Analase is inhibited by fluoride. Fluoride binds to the magnesium in its active site and shuts it down.
And that's why fluoride is in toothpaste. It messes with bacterial glycolysis so they can't make acid and rot your teeth. Smart chemistry.
Ding ding ding. That's right, Sad. Now last step, step 10, pyruvate kinase. This is where we cash in that high energy PEP for our second ATP. Pyruvate kinase transfers the phosphate from PEP to ADP, making ATP and pyruvate.
Okay, so the final tally from glycolysis. 2 pyruvate, 2 net ATP, and 2 NADH per glucose molecule.
Yep, and just to lock in the regulation, pyruvate kinase is activated by fructose 1,6 bisphosphate. That's a feed-forward activation, since it's made earlier by PFK1. It's inhibited by ATP. In the liver, glucagon can phosphorylate it and turn it off during fasting to save glucose.
Got it. Now what happens to that pyruvate? That's where the aerobic versus anaerobic fork comes in, right?
Right, it all comes down to oxygen. If oxygen is present in an aerobic environment, pyruvate enters the mitochondria. There, the pyruvate dehydrogenase complex converts it to acetyl-CoA, carbon dioxide, and NADH. Acetyl-CoA then enters the TCA cycle. If oxygen is absent in an anaerobic environment, pyruvate stays in the cytosol. Lactate dehydrogenase converts it to lactate, and in the process, it regenerates NAD plus from NADH. So glycolysis can keep running.
So aerobic just yields more ATP, but it's slower. Anaerobic is the fast emergency route. Just 2 ATP per glucose, but at least it doesn't need oxygen, right?
Exactly. It's the body's backup generator for when the main power is out.
So when does this emergency anaerobic plan become the main plan?
3 classic high yield scenarios. Red blood cells, they have no mitochondria. Anaerobic glycolysis is their only source of ATP forever. Vigorous exercise, your heart and lungs can't deliver O2 to muscles fast enough. They switch to anaerobic for rapid ATP. Ischemia, like in a heart attack or a stroke, blood flow and oxygen is cut off. Anaerobic glycolysis is a temporary survival pathway.
Okay, so I know it doesn't need oxygen, which is awesome, but there has to be some downside. Is there anything else besides low ATP yield?
Lactic acidosis. Lactate releases a proton if you make too much too fast, like in severe shock, respiratory failure, or overwhelming sepsis. The H plus piles up, blood pH drops, and you get a dangerous metabolic acidosis.
Okay, ladies and gentlemen, once again, let's try a clinical application question. A patient is brought in after a prolonged heart attack. Blood work reveals a severe metabolic acidosis with a significantly elevated serum lactate level. Which of the following best explains the primary cause of the lactic acidosis? A. Increased activity of the pyruvate dehydrogenase complex. B. Impaired function of lactate dehydrogenase, or LDH. C. Switch to anaerobic glycolysis in hypoxic tissues. D. Overactivation of the TCA cycle in mitochondria. Once again, lock in your votes. Let's see what you think, Yahya.
And the answer is C. This is a classic high yield scenario. During a heart attack, blood flow and therefore oxygen delivery to the heart muscles is severely reduced. Without oxygen, cells can't use the electron transport chain. They're forced to rely on anaerobic glycolysis to make ATP even though it's inefficient. The enzyme lactate dehydrogenase then converts the resulting pyruvate into lactate to regenerate NAD+ and keep glycolysis going. This reduces lactate and hydrogen ions faster than the liver can clear them, leading to a dangerous drop in blood pH.
Thank you so much, Yahya, for running us through the question. Let's go on to the next stop of our journey. When we have oxygen available, our pyruvate from glycolysis enters the mitochondria. What's waiting for it?
A gigantic, beautifully organized machine called the pyruvate dehydrogenase complex. Its job is to perform bridge surgery. Convert the 3-carbon pyruvate into 2-carbon acetyl-CoA, which is the only fuel the TCA cycle accepts. In the process, it releases 1 carbon dioxide and makes 1 more NADH.
You called it a complex. Why?
Well, Saad, it's not just one enzyme. It's 3 core enzymes working in a perfect sequence, and it requires 5 different coenzymes to help. It's just goated like that. This is a classic high-yield fact. The mnemonic is the lovely coenzymes for nerds. That is for thiamine pyrophosphate, which is made from vitamin B1 or thiamine. Lovely is for lipoic acid. Coenzyme, well, it's just coenzyme A, and it's made from pantothenic acid, which is vitamin B5. 4 is for fat, from riboflavin, which is vitamin B2. And finally, nerds is for NAD+, from niacin or vitamin B3.
The mnemonic really isn't doing med students a favor, but hey, a deficiency in any of these B vitamins can jam this gigantic, beautifully organized machine, right?
Yes, Sad. The big one is thiamine B1 deficiency. If you don't have TPP, PDH breaks down. This is huge in malnourished patients or alcoholics. If you give them IV glucose load before thiamine, you force glycolysis, which makes pyruvate, which hits the broken PDH gates and back everything up. This can precipitate or worsen Wernicke-Korsakoff syndrome, a devastating neurological condition.
So the rule is thiamine before glucose in at-risk patients?
Always. Now, how is this PDH complex regulated? Remember, it's the gatekeeper to the high-efficiency TCA cycle.
I'm guessing the cellular energy change?
You got it. It's regulated by phosphorylation. A PDH kinase turns the complex off by phosphorylation when energy is high. High ATP, high NADH, high acetyl-CoA. A PDH phosphatase turns it on by dephosphorylation when energy is low. high ADP, high calcium ions, like in a contracting muscle needing energy.
You also mentioned that fatty acids play a role, right?
Yes, this is the glucose fatty acid cycle. When fatty acids are being broken down, they produce lots of acetyl CoA and NADH. These products inhibit PDH. So when fats are fueling the cell, it politely tells glucose, thanks, but we're good for now. This spares glucose for cells that need it, like neurons.
Acetyl CoA is going through the gate. It enters the TCA cycle in the mitochondrial matrix. What's the goal here?
To fully oxidize or completely burn those two carbon atoms from acetyl CoA down to carbon dioxide, and in the process, capture as much energy as possible in the form of electron carrier buses. Per 1 acetyl CoA, the cycle produces 3 NADH, 1 FADH2, and 1 GTP, which is basically ATP.
I heard that this cycle is called amphibolic. What does that even mean?
Well, amphi means both, and it's both catabolic, breaking down acetyl CoA for energy, and anabolic, providing building blocks for biosynthesis. It's the central hub where all fuels, carbs, fats, proteins meet, and where the cell can grab intermediates to build other things.
Walk me through some of these exit ramps.
Sure, citrate can leave to make fatty acids and cholesterol. Alpha ketoglutarate can become glutamate, a precursor for other amino acids and neurotransmitters. Succinyl CoA is used to make heme, the core of hemoglobin. Oxaloacetate can be used to make glucose via gluconeogenesis or amino acids.
Okay, Yahya, I have a question. So, if the intermediates are constantly being pulled out to build stuff, why does the cycle keep turning? It should probably run out of parts, right?
Brilliant question, Saad. This is where anaplerotic reactions come in. They refill the cycle. The superstar here is pyruvate carboxylase. It takes pyruvate and, using energy from ATP, adds a carbon dioxide to make oxaloacetate. And guess what activates this enzyme? Acetyl CoA.
Wow, what a beautiful feedback loop.
It is. If acetyl CoA builds up, maybe because the cycle is slow, it activates pyruvate carboxylase to make more oxaloacetate, which helps pull acetyl CoA into the cycle. It's like the cycle saying, I need more workers to handle this load.
I'm getting really tired of these work analogies. I thought you didn't have a job. Anyways, so we've got acetyl CoA entering the TCA cycle, and it's spinning around, cranking out NADH, FADH2, and GTP. But this isn't some just runaway train, right? There's got to be control points along the way. Places where the cell can press the gas or hit the brakes depending on its energy needs.
Exactly. The TCA cycle is tightly regulated, and there are a few key enzymes that act as checkpoints. The big one is isocitrate dehydrogenase.
That sounds important. Is it the rate limiting step?
Yep, Saad, it's the rate limiting step of the entire TCA cycle. It's the one that sets the overall speed, and just like you'd expect, it's exquisitely sensitive to the cell's energy status.
Okay, so I know that it's the rate limiting step, but what turns it on and off?
It's activated by signals of low energy such as ADP and calcium. ADP says, we need more ATP, let's rev this up. Calcium, especially in muscle cells during contraction, is like a direct signal to ramp up energy production.
And what slows it down?
The classic signals of high energy, ATP and NADH. If the cell is already energy rich, isocitrate dehydrogenase gets the message to take it easy and not burn fuel unnecessarily. It's a perfect example of feedback inhibition.
So that's enzyme number 1. What about the others?
Next up is alpha ketoglutarate dehydrogenase. This one's really interesting because it's like a cousin to the pyruvate dehydrogenase complex we talked about at the mitochondrial gate. They're not the same enzyme, but they work in a similar way and use the exact same set of the 5 coenzymes: TPP, lipoic acid, coenzyme A, FAD, and NAD+.
The lovely coenzymes for nerds.
You got it. So alpha ketoglutarate dehydrogenase is also regulated by energy charge. High levels of its own products like succinyl CoA and NADH will slow it down. It makes sense. The cycle's later products are piling up. You don't really need to make more of them, right?
What about GTP? Where do we make that in the cycle?
I'm so glad you brought this up, Sad. You're very good at bringing up things.
Oh, thank you.
No worries. GTP is made by succinyl CoA synthetase. This is the step where succinyl CoA gets converted to succinate. In the process, the high-energy thioester bond in succinyl CoA is used to phosphorylate GDP, making GTP. This is the only substrate-level phosphorylation in the entire TCA cycle. ATP made directly in the mitochondria, independent of the electron transport chain.
And then we come to a real 2-for-1 special, right?
Oh, you mean succinate dehydrogenase? This one is super cool. It has a day job in the TCA cycle, converting succinate to fumarate and producing FADH2 in the process.
Damn, it has 2 jobs? I don't even have one. But I'll hear you out. Does this succinate dehydrogenase also moonlight somewhere else?
Yes, my dear Saad, it does. Succinate dehydrogenase is also known as complex 2 of the electron transport chain. It's embedded right there in the inner mitochondrial membrane. It takes the FADH2 it makes in the TCA cycle and passes those electrons directly into the ETC.
That's a brilliant bit of metabolic design. No middleman.
Right? And because it uses fat derived from riboflavin vitamin B2, a deficiency here causes problems. Without enough riboflavin, the enzyme struggles. That's why B2 deficiency shows up with signs like cracked lips, chylosis, and a sore inflamed tongue, which is glossitis.
Okay, let's recap the TCA regulation. So we have isocitrate dehydrogenase, which is the rate-limiting boss. It's activated by low energy like ADP and calcium, while also being inhibited by high energy like ATP and NADH. We also have alpha-ketoglutarate dehydrogenase, PDH's cousin, which uses the same 5 coenzymes regulated by energy and its own products. Then we have succinyl-CoA synthetase, which makes GTP via the cycle's only substrate-level phosphorylation. And last but not least, succinate dehydrogenase, which is the double agent. TCA enzyme in ETC complex 2 requires vitamin B2.
You nailed it. It's not just a mindless loop. It's a highly responsive, integrated system that perfectly matches energy production with the cell's moment-to-moment needs.
Okay, now let's lock this in. Here's the case. A 60-year-old man with a history of heavy alcohol use is brought in by his son. He's disoriented, stumbling, and has nystagmus. You order IV fluids in labs, and you remember a critical rule. Give 1 vitamin before starting the IV with glucose to prevent a neurological emergency. Which vitamin is this, and what's the biochemical reasoning? A. Niacin, vitamin B3, needed to make NAD+ for lactate dehydrogenase. B. Riboflavin, vitamin B2, which is a cofactor for succinate dehydrogenase. C. Pantothenic acid, which is vitamin B5, required to form CoA for the TCA cycle. D. Thiamine, vitamin B1, an essential cofactor for the pyruvate dehydrogenase complex. Let's hear what you have to say, Yahya.
And the answer is D, thiamine or B1. Thiamine deficiency is common in alcoholism. Thiamine pyrophosphate is the cofactor for pyruvate dehydrogenase synthesized from thiamine. And always remember, give them thiamine first and then glucose.
I'm getting a bit tired here, but we finally finished the TCA cycle. We have a bunch of full electron buses, NADH and FADH2. They've been carrying the high energy electrons stripped from our original glucose. Now what?
Now we go to the cell's true power plant, the electron transport chain, or ETC, located in the inner mitochondrial membrane. This is where we cash in those lovely electron buses for the big prize, ATP.
Paint a picture of this ETC for me.
Now I want you to imagine with me, Saad, we have a series of 4 protein complexes, 1, 2, 3, and 4, embedded in the membrane, with 2 mobile carriers, coenzyme Q and cytochrome C, shuttling between them. NADH drops its electrons off at complex 1, FADH2 from the succinate dehydrogenase enzyme drops off at complex 2. The electrons are then passed down the chain from complex 1 or complex 2 to coenzyme Q, and then to complex 3, and then to cytochrome C, and then to complex 4, like a bucket brigade.
Okay, so from complex 1, coenzyme Q takes it to complex 3, and then we said cytochrome C takes it to complex 4. So where does all of this finally end up?
At the very end, at complex 4, the electrons are handed to oxygen, which combines with hydrogen ions to form water. This is why we breathe oxygen.
And passing these electrons down releases energy? What's the energy used for?
This is the genius part. The energy released at complexes 1, 3, and 4 is used to pump protons from the mitochondrial matrix across the inner membrane into the intermembrane space. This builds up a proton gradient.
Oh, so it's like using electricity to pump water uphill into a reservoir.
Exactly. That reservoir is full of potential energy. The only place the protons can flow back down into the matrix is through a special turbine called ATP synthase, sometimes called complex 5. As the protons rush through, they spin the turbine, and that mechanical energy is used to take ADP and PI and forge them into ATP.
So this whole process is called oxidative phosphorylation?
Yep, the oxidation of NADH or FADH2 is coupled to the phosphorylation of ADP to ATP. This process generates about 90% of the cell's ATP. It's incredibly efficient.
Okay, but something feels unfair. Why does NADH give about 3 ATP, but FADH only gives 2?
Because FADH2 drops its electrons off at complex 2. which is after the first proton pumping station, or complex 1. So its electrons only drive proton pumping at complexes 3 and 4, yielding less ATP. NADH gets the full ride from complex 1.
This sounds like an elegant but delicate system. Is it possible that something happens if we rake it?
Yes, Saad, some poisons and drugs target specific parts. They're classic exam fodder. We have inhibitors that block the flow of electrons, such as retinone, which blocks complex 1, cyanide and carbon monoxide, which block complex 4, oligomycin, an antibiotic that blocks the ATP synthase turbine.
Okay, so if you block the ETC, what are the downstream effects of this?
Well, electrons can't flow to oxygen, the proton gradient collapses, no ATP is made, the cell panics and switches entirely to anaerobic glycolysis, leading to a massive, rapid lactic acidosis. Cyanide poisoning, for example, presents with headache, confusion, and the classic bitter almond breath smell.
What about uncouplers? That sounds different.
It is. Uncouplers don't block the ATC, they short circuit the proton gradient instead. They let protons leak back into the matrix without going through ATP synthase. So the ATC keeps running at full speed using oxygen and NADH, but no ATP is made. All that energy is released as heat instead.
That sounds dangerous, but also useful?
Well, absolutely. The drug 2,4-dinitrophenol is a potent uncoupler. It was once used as a weight loss drug because it makes you burn fat like crazy, but it's lethally dangerous. It can cause fatal hyperthermia. But naturally, we have an uncoupler called thermogenin, or UCP1, in brown adipose tissue. Babies and hibernating animals use it to generate heat to stay warm without shivering. It's a brilliant adaptation.
Okay, now that we've done all this, maybe it's finally time to tie all of this back into medicine. Walk me through some of the high-yield clinical correlations.
I would love to, Saad. Lactic acidosis, we've covered it. Hypoxia or ischemia will lead to an increase in anaerobic glycolysis, which will lead to an increase in lactate or hydrogen ions, and therefore decreased pH. Pyruvate kinase deficiency, this is a glycolysis enzyme defect. RBCs which rely solely on glycolysis can't make enough ATP. Their sodium pumps fail, they swell up, and you get a chronic hemolytic anemia. Interestingly, they also have high 2,3-BPG, which shifts the oxygen dissociation curve to the right, helping deliver more oxygen to the tissues to compensate for the anemia. Vitamin deficiencies. Bear with me, Saad. This is gonna take a while. B1 or thiamine deficiency will lead to beriberi, and not to confuse it with the chicken sandwich, and Wernicke-Korsakoff. B2 or riboflavin will lead to chylosis, glossitis, and impairment in succinate dehydrogenase and other flavoproteins. B3 or niacin will present with pellagra, or the 4Ds, dermatitis, diarrhea, dementia, and death. And finally, the Warburg effect. Cancer cells, even in the presence of oxygen, prefer to use anaerobic glycolysis, converting glucose to lactate. It's inefficient for ATP, but it provides building blocks like those TCA intermediates for rapid growth and division. This is a metabolic signature of many tumors.
Whew, that was a lot. Let's take a deep breath quickly and just recap the journey of one glucose molecule.
Let's do it. So, glucose first enters the cell via GLUT transporters. An important thing to remember here is that insulin regulates GLUT4. Glycolysis then takes place in the cytosol, where glucose is converted to 2-pyruvate, 2-net ATP, 2-NADH, and the PFK1 here is the rate-limiting step. And then comes the fork. If we have low oxygen or an anaerobic environment, pyruvate is converted to lactate via lactate dehydrogenase, and NADH is converted to NAD+, and this yields us 2 ATP molecules per glucose. However, if we have a normal oxygen environment or an aerobic environment, pyruvate goes to the mitochondria, into the PDH complex, where pyruvate is converted to acetyl-CoA, NADH, and carbon dioxide. It's important to know here that PDH complex uses the 5 cofactors, or the lovely coenzymes for nerds. Always remember, it's regulated by phosphorylation. Next up is the TCA cycle, and this takes place in the mitochondrial matrix, where acetyl-CoA is converted to 2 carbon dioxide molecules, 3 NADH, 1 FADH2, and 1 GTP. And isocitrate dehydrogenase here is the rate-limiting step. And also remember here that the TCA cycle is amphibolic. And finally, electron transport chain and oxidative phosphorylation in the inner mitochondrial membrane. NADH or FADH2 donate electrons that release energy as they flow through the ETC, releasing energy that pumps hydrogen ions into the intermembrane space, creating a proton gradient. Hydrogen ions then flow through the ATP synthase back into the mitochondrial matrix, making ATP. And this gives approximately 30 to 32 total per glucose.
And regulation is woven throughout via energy changes, right? ATP and AMP, allosteric control, covalent modifications like phosphorylation, and hormones like insulin and glucagon, right?
Exactly. It's not a set of isolated steps, it's an integrated, responsive energy network.
Wow. Thank you so much for this amazing recap, Yahya. Okay, so now let's have some rapid fire review questions. Aerobic versus anaerobic. Which makes lactate?
Anaerobic.
What's the only TCA enzyme also in the ETC?
Succinate dehydrogenase or complex 2.
Cyanide black switch complex.
Complex 4.
Delivers glucose sensory enzyme.
Glucokinase.
Natural uncoupler in baby fat?
Thermogenin.
Wow. Saraha, you've actually surprised me. That basically makes a wrap for today's PodBite episode on the cell's energy factory.
If you remember nothing else, remember this. Every bite of food, or that beautiful beta shawarma you just ate, sets off an adventurous, tightly regulated journey from a sugar molecule to the ATP in your beating heart. It's a story of transformation, regulation, and survival.
Thank you so much for tuning in. If this episode helped you connect glycolysis to the clinic, maybe share it with a friend who's crying in the room over their mole exam.
And don't forget to stay curious and keep learning one bite at a time.
And that's why fluoride is in toothpaste. It messes with black... My flow state is gone.
Step 6 is massive. I'm gonna say it.
Not gonna say it?
I'm not gonna say it.
Okay, I'm gonna say, okay.
Hold on. Step 6 is massive. Just like the low taper fade.
Just get to the... If you don't want to say it, I'm gonna say it, by the way.
Does anyone get it?